Hello, welcome back to this lesson in dealing with logarithms. The title of this lesson is called Solving Logarithmic Equations. If you go up to a random person and you say, you know what, we're going to talk about solving logarithmic equations, most people are going to think you're crazy, or they're going to think that whatever you're talking about is extremely complicated. Well, what we're going to do is we're going to learn how to solve equations that contain logarithms. Another way to say that is logarithmic equations. And by the end of it, once you get practice with it, I hope you'll understand that it's not really very much more involved than solving regular equations in algebra. The things that you have to keep in the back of your mind in order to solve any equation that contains a logarithm is mostly that you have to understand the laws of logarithms. Now, actually, I did several lessons on the laws of logarithms in the last couple of lessons, so if you haven't watched those, you really have to understand that in order to get this. I went ahead and erased them from the board because we need to commit them to memory anyway, and so ultimately you need to have them in your mind. The number one thing you need to know is that whenever you have a logarithm, you can kill that logarithm or annihilate it by raising that logarithm to an exponent with the same base, because the exponential function and the logarithmic function are inverse functions of each other. So whenever you do the opposite function, then you annihilate and it disappears. And that's one way that we're going to use to solve these equations. Other than that, you have to understand the laws of logarithms. What happens when you multiply something together? It becomes addition of logarithms. What happens when you divide something? It becomes a subtraction of logarithms, and so on and so forth. So we have to just go ahead and do it. And that's what we're going to do here. Let's take a look at our first problem. Logarithm base 3 of some number x plus logarithm base 3 of some number x minus 6 is equal to 3. Now this is what we call a logarithmic equation. It has an equal sign, so it's an equation, and it contains logarithms. Now in this case, the unknown quantity is x, but that x appears in two locations. So what we have to do for these kinds of equations is very similar to regular equations. We want to isolate and get x on one side of the equal sign all by itself. That's all we want to do. And we're going to have to use the laws of logarithms to do that. So we see immediately we have a term over here, that's a logarithmic term, and a term over here. It's the same exact base. And we know that when we add logarithms together, we can combine them to basically one single term as follows. You can combine it like this. It has to be a logarithm, base 3 of x, which is this term, times x minus 6, which is this term. And that's going to be equal to 3. If you do not understand this step, then it just means you never watched the lessons on the laws of logarithms. You can think of it going backwards. We have things multiplied, two things multiplied, this term times this term inside of a logarithm, so we can break it out into addition of those logarithmic terms. That is a law of logarithms we've already learned in the past. So now we have to continue to multiply through to get x by itself. Log base 3, this is going to be x squared minus 6x on the inside, just multiplying the x through, and then we get equal to 3. All right, so as often happens in math, there's almost always multiple ways to proceed. When you solve equations, there's lots of different paths you can take. So when you get to logarithms, there's actually even more paths you can take, and they all should get to the same answer. So if I'm doing something here and you're thinking, oh, I'd rather do it a different way, that's fine. Do it your way. As long as you get to the same answer, I'm fine. Now, in some of these problems, I'm going to go ahead and work the problem two completely different ways because I want you to understand that no matter what you pick, as long as you're following the correct rules, you're always going to get to the same exact correct answer. All right, so there's two ways to proceed. I'm going to call this first one method. It's not really a method, but it's kind of the way I'm doing it, number 1, and then over here I'll do number 2. So what do I have? This is a logarithm. It has a base 3, so I can write 3, which is the base, to the power of 3, which is what's on the right-hand side, is equal to what I'm taking the logarithm of, x squared minus 6x. You see, in this way, I've completely eliminated the logarithm from the equation. It's gone. So that logarithm, where the variable is wrapped up inside of that logarithm, it's now gone. I don't have to worry about that because I used the definition of the logarithm. The base to the power of whatever the logarithm returned is equal to this, and that is just simply a polynomial now. So what you have is you have x squared minus 6x. I'm going to move this to the other side, so it'll be a minus sign, and 3 times 3 is 9. And so what you're going to, actually not 3 times 3 is 9, it's 3, not 3 squared, it's 3 cubed, so you're going to have 27, sorry about that. So we subtract it, bring it over here, it's going to be a negative sign, 27, and that's equal to 0. So now your logarithmic equation just now reduced to a polynomial that we've solved many, many times. So let's try to factor this thing. Open up parentheses equal to 0. X times x. We can pick whatever you want here, but ultimately 9 times 3 is going to work. We need a minus sign, and we need a minus sign here, so the way that's going to work is minus and plus. Double check yourself. X times x is x squared. This times this is negative 27. Here's a negative 9x. Here's a positive 3x. You add that, you get a negative 6x. So it appears that we have two solutions. We have x minus 9 is equal to 0, so x can be equal to 9. And we have x minus 3 is equal to 0, and that means x is equal to 3, right? Actually, there's a plus sign here, sorry about that. So this could be a negative right there. So it appears that we have two solutions. X minus 9 is 0, x plus 3 is 0. So x can be 9 or x can be negative 3. So if you were to circle those answers, you would actually be wrong, or at least partially wrong. Can you spot what the problem is? It's kind of tricky, but the problem is this negative sign here, right? Remember what you're doing. You're trying to find the values of x that satisfy the original equation that you have, which is this one. X appears here and x appears here. But when you look at the plot of the logarithm function, a logarithm is never, ever, ever defined when you stick a negative value into that logarithm. It doesn't exist, or at least it doesn't exist in terms of real numbers. Why is that? If you remember back to the plot of a logarithm, it's the inverse of the exponential function, right? So if this is x and this is f of x, and we're plotting a logarithm here, then what's going to basically happen is it goes through the number 1, that's this spot right here. It starts very close to the axis, it goes through this point, and then it bends over something like this. So this is an asymptote. It never really gets to the axis right here. So these are negative values of x, negative 1, negative 2, negative 3, and this is positive 1, positive 2, positive 3, and so on. So the logarithm has values for 1, 2, 3, 4, 5, 6, 7, and all also very, very close to 0, like 0.5, 0.3, 0.1, 0.0001. But it does not exist over here. You cannot put a negative value into a logarithm. And this comes about because this logarithm is a reflection of the exponential function. It's a reflection of an exponential function across this diagonal line y is equal to x. So if you can imagine an exponential function doing something like this, then reflecting it gives the inverse, and that's why it's down here. So just like an exponential function doesn't exist down here, a logarithmic function does not exist over here because it's a reflection. So what you need to know is that negative values are not allowed to be stuck into logarithms, and so you cannot have a negative value like this. So what you say is not a solution. If you take a negative 3 and try to stick it in a calculator, it's going to give you an error because it's not defined. It doesn't exist. It's like saying, give me a square rectangle. A square triangle, or give me a square circle. It's not going to work. It's not defined. So we throw away this and we say, this is our solution. We have one solution of this equation. All right, one solution of this equation. If you stick the number 9 in here and calculate this log and here and subtract and calculate this log and add it, then you're going to get the number 3. Now that was method number 1 using the definition of the logarithm. There's always different ways to do a problem. So I want to talk briefly about what I'm going to call method number 2. Because there's always more than one way to do something. So let's go around here and try to keep things as tidy as I can. Okay, so we have this logarithmic equation here. We combine the logarithms, we get down to this point. This is the point where we branch off and we say there's 2 methods. What else can we do at this step right here? Remember, we talked about the fact that a logarithm is the inverse function of an exponential. They are opposites of one another. They annihilate each other. They kill each other. They undo each other. Whatever word you want to do, the opposite of a logarithm is an exponential. The opposite of an exponential is a logarithm. We've done problems like this in the past, but this is the first time where we're going to solve kind of a more complicated equation using this. So if I don't want to do this, but I want to start at this point, then what I can do is since this is a logarithm that I want to get rid of, I can raise both sides with a base of 3. I can say 3 to the power of logarithm base 3, x squared minus 6x, is equal to 3 to the power of 3. You see what I've done? I can do anything I want to both sides of this equation, as long as I'm doing it to both sides. I choose to raise the left hand and put it in the exponent of a 3. And the right-hand side, I'm going to also put it in the exponent of a 3. So basically the equation is still balanced. I've raised both sides to the power of 3. But here I have a power of base 3, and then in the exponent I have a logarithm base 3. So the exponential base 3 cancels or annihilates or kills the logarithm base 3, and all I have left down here is x squared minus 6x. Poof! It's like you could draw a line through the log and through the base, and this is what I have left, equals, not 9, I keep wanting to say 9. This is 3 cubed is 27. Look at what I've written down here. X squared minus 6x is equal to 27, which is exactly what I have here. X squared minus 6x minus 27 is equal to 0. It's exactly the same polynomial we wrote down right here. So whatever way you want to do, I want you to do that. However, I do want you to start thinking about, oh, I want to kill that logarithm. I want to raise that thing to an exponential. Oh, I want to kill that exponential. I'm going to take a logarithm of that boy, because then I can get rid of it, right? I know that it doesn't really seem like it's something you want to do in these kinds of problems here. It seems like maybe it's easier to do it this way, and whatever you want to do. But I'm telling you that as you get to more complicated problems, you're going to want to annihilate and eliminate both sides of an equation by doing the opposite or the inverse operation. And that means if you have a log, then you take the exponential of both sides to kill that log, and so on. And you get exactly the same solution either way. We're not going to do that every single time. I'm not going to solve the problem twice every single time, but a few times along the way I will do that. Problem number 2. Let's say we have logarithm, and here's something weird. The base is actually not a number, it's a letter. Call it a. I'll explain in a second. Of the variable x is equal to 2 times the logarithm base a of 3 plus logarithm base a of 5. All right, so you might look at that and say, I've never seen an equation like that. It makes no sense at all. Well, it's because you haven't seen it before. So once you see it the first time, it's not so scary. What's going on here is, normally we have bases of logarithms, base 2 logarithm, base 3 logarithm, base 10 logarithm, whatever. Here I'm just saying, I don't care what the base is. It's base a. Some number is here. I don't know what it is, but it's something. And whatever that is, it's the same base for this logarithm, and it's the same base for this logarithm. A is not what I'm trying to solve for, though. I'm trying to solve for the variable x. X is my unknown. It just so happens that in this equation, base a, base a, base a doesn't actually matter. You're going to find out as we do the solution that the base, the particular base of this logarithm, it doesn't matter. If I have a base 2 in all 3 of those locations or a base 10 in all 3 of those locations, the answer will be the same. So don't let that stress you out. Just treat it as a base and follow the rules of logarithms. What do I want to do? Again, there's a couple of different ways I'm going to do this, but let's start working on the right-hand side. Let's say on the left, log a of the unknown variable x. Here I have a 2 times log, so I'm going to bring that 2 and put it in the exponent. That's one of the rules of logarithms that we learned in the past, that I can take an outside multiplier number and move it into the exponent on the inside of a logarithm, like this. And then I have log, again, base a of the number 5. So on the right-hand side, I have a logarithm plus a logarithm, and I can now combine those. Logarithm, base a of the number x, logarithm, base a of, 3 times 3 is 9, times the 5. So I'm basically multiplying inside, because multiplying on the inside of a logarithm becomes addition of logarithms. So when I continue, I have log base a of 45. And now you see exactly what the solution of the equation is. I have a base a logarithm on the left and a base a logarithm on the right. It's the same exact logarithm, same exact base. So the only difference between the two is what x is, and it has to be equal to 45. And that's how you write the answer now. I got it into a position where everything else was the same, so that x had to be equal to what I can read off on the right-hand side of the equation, right? And now you can see that it doesn't matter what base you put in here. If I chose this to be base 2, and base 2, all that would happen is I would get base 2 here and base 2 here. X would still be 45. If I choose a base 10, 10, and 10, all that's going to happen is this will be base 10 and base 10. X will still be equal to 45. Don't get so wrapped up when you see that you don't think you can get to the end from the beginning. You have to just start working and start carrying things through logically. Okay? Now there's always more than one way to do something, and I want to show you that way. Let's write the equation over again. Log base a of x, 2 times log base a of 3, plus log base a of 5. All right? So I told you. I said, ultimately I want this x variable over here. So forget about the rest of this thing. I want x by itself. But x is wrapped up inside of a logarithm, a base a logarithm. How do I get x by itself? It's wrapped up inside of a package. How do I get rid of that logarithm? Well, I have to do the inverse, the opposite function. The opposite of a logarithm is an exponential function. So if I take the left-hand side and I say base a, and I raise it and put this thing in the exponent, base a of x, I have taken what I have and I've raised it to the exponential of the base a exponential. So I have an exponential and a logarithm up here. They cancel each other. So that's how x is going to drop out on the left. But I have to do the same operation on the right-hand side. So it would be a to the power of 2 times log a 3 plus log a base a 5. I know it looks crazy. All I'm doing is I'm raising the left-hand side of the equation to the power, a to the power of that, and then a to the power of this. But the nice thing about it is because log is exactly the inverse of a, then on the left-hand side, the only thing left is x. It drops out. It's like it cancels with it. Just like 4 over 4, they cancel. 5 over 5, they cancel. 10 over 10, they cancel. A to the power of log a, they cancel. So the x drops out. On the right-hand side, I have all of this stuff. But notice that in the exponent here, I have a plus sign. So I can write this exponent as a to the power of 2 log base a 3 multiplied by a log base a 5. How can I write it as a multiplication? Because these exponents are added. So because the base is the same, I can add these exponents, which is exactly what I would have here. So I'm just breaking it up, going in reverse. I have an addition of exponents, so I'm going to treat it as multiplication. And I can add these exponents and get what I have there. Right? So now notice what's going on. Over here I have 2 times log base a of this, so I need to take care of that. So it'll be a log base a 3 squared. This floats in front and goes into the square here because it's sitting outside of a logarithm. That's another one of our rules of logarithms in dealing with exponents. Multiplied by a raised to the power of log a to the 5th. Not to the 5th, log of the number 5. So here we're very close. We have x on the left. What do we have on the right? The a raised to the power of log base a, the logs in the a completely cancels. All I have is 3 squared. This cancels, I have the number comes and drops down. The a and the log base a cancel here, leaving me with 5. Now I have 9 times 5, x is equal to 45. It's exactly the same answer we got here. Now you might look at this and say, oh, there's more steps. I don't like that. Oh, there's fewer steps. I like this. I'm trying to show you both ways, mostly so you understand how it's done. Because later on, some equations will be really hard to solve this way, especially in advanced calculus. So I'm trying to teach you, the path to get from here to there. All right, you get the same answer either way. But you have complete freedom on how to proceed as long as you're following the correct rules. All right, let's go back to a little more of an easier problem. Let's say we have logarithm base b of x plus 3. I don't know what the base is. I don't care. It's some number b equals log base b of the number, let's see if I can erase this, of the number 8 minus log base b of the number 2. All right, so there's lots of different ways to do this. I'm not going to solve every problem 2 ways, right? But you'll by now know that there's 2 ways to do it. I can use the laws of logarithms, which is how most textbooks will probably show you. Or I can, because I want this variable x to pop out, I can raise both sides, base b raised to this, and then base b raised to that, and I'll get the same exact answer either way, just like I did in the last problem. So you have to pick a way. There is no correct way. I will do some problems one way and some problems another way. This way, let's just use the laws of logarithms. Log base b x plus 3. On the right-hand side, what do we have? A subtraction of logs. So I can write this as log base b of 8 over 2, because this minus this becomes division, 8 over 2. So what I'll have is log base b x plus 3 equals log base b of what? 4. Now you see what you have. Log on the left, log on the right. Base b, everything's the same. So that means this thing inside of the log has to be equal to 4. X plus 3 is equal to 4. So then x, when you subtract the 3, you just get a 1. This is the final answer. Now I'm not going to solve every problem every way, but if you were to do this the other way, if you would raise the left-hand side b to the power of this, and the right-hand side b to the power of this, it would look really, really similar to what we did here. It's almost the same exact problem. Everything would fall out so that you would still get x is equal to 1. And from now on, I'm just going to pick a path. I'm not going to particularly choose one specific way to do things. Okay? Let me slide to the next board to do the next problem because it's a little longer, and then our last problem is actually going to be fairly short. What if we have log base a of the variable x minus log base a x minus 5 is equal to log base a of the number 6. Again, I can do what I want. I can use the laws of logarithms. I have subtraction of two logarithms. I could do that. It would probably be a shorter answer, just like I did in the last one. But I really want you to understand both ways of doing it. So instead of doing it like this, where we use the laws of logarithms, it'll probably be pretty short, to be honest with you. Let's do it the slightly longer way, because I want to show you that both ways work. All right? So here I have log base a, log base a, log base a. Right? So what I want to do is I want to kill all those logarithms. So on the left-hand side, I'll raise it and put all of this stuff in the exponent of a base a. This whole thing on the left-hand side, a x minus 5. This entire thing is in the exponent of a. Over here, a log base a 6. All right? But again, I have a subtraction. In the exponent, I have subtraction. So I can write this as log in the exponent, a of x multiplied by a to the, how do I want to do this? Negative log a, base a, x minus 5. And on the right-hand side, the a is going to kind of cancel with the log a because they're inverses of one another. I'm just going to have a 6. Now make sure you really understand the left-hand side. All I'm saying is that I have the same base here, so I can add these exponents. If I add this to this in the exponent, I'm going to get exactly what I had before. That's why I had to have the negative sign there, because ultimately they're subtracted. So I can work in kind of the exponential kind of realm if I want to. Now what do I have? This log base a cancels with this exponential with base a, so I just have the x popping out from the top. This a cancels with this. However, there's one little gotcha here. You have a negative sign in front. Before you can do the cancellation, this is like a negative 1 out here. So what I want you to do is say log base a x minus 5 to the negative 1 power. This is like a negative 1 times this. So forget about everything else here. If you just had this negative 1, you can float it in and put it as a power. Log base a x minus 5 to the negative 1. Log base a x minus 5 to the negative 1. I want to get rid of it here and bring it here, so now I have a very clean cancellation. A canceling with log. This is equal to 6. So I'm going to have x multiplied by the a as a base cancels with log a, so all I have left is x minus 5 to the negative 1. Let me just double check myself. And so now I'm home free. I've got rid of all the logarithms. Now it's just a basic algebra problem. Let's bring this to the bottom. X over x minus 5 to the first power. I can drop the parentheses or leave them there, whatever you want. 6. So I have to solve for x. So I'm going to multiply the left and the right-hand side by the denominator x minus 5. On the left, I'm going to be left with x. On the right, it'll be 6 times x minus 5. I multiply the left by x minus 5. It cancels. That's what I'm left with. On the right, I multiply by the same thing. Here's what I have. So I have now 6x minus 30 when I distribute this in. And then I'm going to move the 6 over here by subtraction. So 1 minus 6 is negative 5x. And then I'm going to divide by negative 5. I'm going to get a positive 6. X is equal to positive 6. That's correct. All right? And again, there's always more than one way to do the problem. But in this case, I wanted to really show you that you can, if you have logarithms running around your equations, just kill them with exponentials. Raise the left to an exponential, the right to an exponential, same base, and all of those logs will get eliminated. All right? Now, just for giggles, I want to make sure you understand that there's obviously an equivalent way of doing this here. So let's go down here, and I'm going to show you, we're going to start with the black line. How would we do it just using the laws of logarithms? I have a logarithm minus a logarithm. So I can write this as a division. Log base a of this divided by this. X over x minus 5 equals this. Log base a 6. So you see, just with a simple line, I now have base a logarithm, and the thing I'm taking the logarithm of, they have to be equal. X over x minus 5 is equal to 6. This is exactly where I arrived right here. X over x minus 5 is 6. So from here, the solution's the same. You would get the same thing. I agree with you that this is fewer steps. This is typically what you would see, in most textbooks, especially at the introductory level. But I really want you to understand how logarithms and exponentials can annihilate each other, because when you get farther along in math, it becomes incredibly useful. And so I want to make sure you understand that. All right, we have one more problem. It's actually not a very long problem, so I'm going to slide back here and do it underneath. But it's a good problem. What if I have logarithm base 2 x squared minus 9 is equal to 4? Now, I just got through telling you I can kill the logarithm with an exponential. I can raise both sides to an exponential with a base 2. I can do that. But instead of doing that, let's just use the definition of a logarithm, just for variety. 2 to the power of 4 is equal to what this is inside the logarithm, x squared minus 9. Now the logarithm is again gone. 2 to the power of 4 is 16, x squared minus 9. I'll move the 9 over by addition. I'll have 25 equals x squared. I never like having it like this, so let's flip it around, 25. And then we'll go over here. I think you can see what the answer is going to be. X is going to be plus or minus the square root of 25. Because I take the square root of both sides, so x can be 5, x can be negative 5. This is the final answer. X is 5, x is negative 5. You have two answers. You might say, whoa, 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 whoa. You just told me that I cannot have negative numbers feeding into a logarithm. You just told me I cannot have negative numbers going into a logarithm. So why do I have two answers here? Well, here's why. If I put 5 in here, it's squared. That's going to be 25 minus 9. That is what I'm taking the logarithm of, a positive number. If I put negative 5 in here, I still get positive 25. I still get the positive number here. I'm still taking a logarithm of a positive number. So you have to check both solutions. Don't just throw it away if it's negative. Go and see if the solution is requiring you to take a logarithm of a negative number. The original problem would have me feed a negative 3 directly into a logarithm. That's not allowed, so I could just kill it. But here I had to go and check and make sure both were valid. So here we have started the process of learning how to solve logarithmic equations. There is more work to it, and you have to understand the rules and the laws of logarithms, but it's not black magic, and there's always more than one way to do it. So make sure you can solve all of these yourself. If I were you, I'd solve both of them 2 different ways, just to make sure you understand. Follow me on to the next lesson. We're going to get more practice solving more complicated logarithmic equations.